So in this lesson, we learn basically why we needed to memorize the unit circle. So we're going to continue to work with, we have a trig function here, and we're going to focus specifically on how to make these trig functions spit out the values we need. So this is one we saw in the last lesson, right? So we have a trig function which models the velocity of airflow F in liters per second at time t seconds. So I would really just annotate time t, velocity F, because that's what's going to help us solve these. And you might want to make a note here that we're interested in solving all these without a calculator, so we're calculator free for this unit. So those values that you memorize on the unit circle are going to come in handy. So find and interpret, so we're going to write a little sentence about this value f of 5 over 3 once we get it here. So this of course means I replace my t with 5 over 3. Okay, so now I'm going to do order of operations. So order of operations is, of course, PEMDAS. And the thing that you need to know that is maybe new here is that sign sort of acts like parentheses. So anything inside the sign we do first before we evaluate. So we're going to multiply our fractions first, and notice my 5's cancel out real nice, and this becomes sine of 2 pi over 3 times 0.6. Okay, now here is where you may have this value memorized. Hopefully you do. If not, I would get out my unit circle. So hopefully you kept those notes. And remember, what did I want? I want sine of 2 pi over 3. So notice I'm going to just bring the 6 down. And when I take the sine, I don't write the sine anymore. That's a really common error. So sine of 2 pi over 3, well, that is, of course, the y value on my unit circle. It is root 3 over 2. Okay, and then I have this awkward thing where I have like a 0.6 times a fraction. So I'm just going to rewrite 0.6 as 3 over 5 times root 3 over 2. And then I have 3 root 3 over 10 is equal to f of 5 over 3. So I did that all without a calculator. So a couple things are challenging here. One is just multiplying fractions. And then the other thing is making sure you take the sign of the correct value. So anything inside the sign happens first. And then, of course, I'm trying to interpret this. So I'm going to write a little sentence here. At t equals 5/3 seconds, so that was from my f, right? My velocity is my result, which is 3 times the square root of 3 over 10. And then my units match the text, liters per second. So that was a fairly easy example. And because we have those values, we did that work already of memorizing those values in the unit circle. Hopefully that will not be the hard part. Here, we're going to make it a little bit more complicated. So notice I didn't give you a statement in our function notation. I just said the breathing rate. Well, that's my y value. So really what I want is I want some f of t to equal 0.3. Well, I can then set that equal to what I know f is, right? And here, what I want to do is I have a variable x that I'm trying to solve, right? So I need to isolate x. Well, to do that first, I'm going to isolate my sign first. So what I can do is I can divide by 0.6 on both sides. So I get 1 over 2 equals that sine of 2 pi over 5 x. So now I have this equation that I need to solve. And notice my sign spits out a nice even value. So I want an x such that my sign is a positive 1 over 2. Well, remember, sign is my y values, so I can only look at quadrants 1 and 2 for positive y values. And I have 1 sine, 2 sines equal to 1 over 2. So I'm going to drop my sign, and I'm going to actually make 2 different equations. So I'm going to be like, okay, 2 pi over 5x equals pi over 6, and 2 pi over 5x equals 5 pi over 6. And the reason I do that is because these are both going to equal 1/2 when I plug them into sine. So what these spit out, and these are both solutions to my equation, and I just realized I switched variables, we should have been using t this entire time, right? Is, what do we get here? We get 5/12 from my top equation, and we get 25/12. And there's actually more too, right? Because remember, if I go all the way around my unit circle and come back, I get the same values, right? So what I get here, if I add 2 pi, go all the way around, is I get 13 pi over 6. That is also a solution, as is 17 pi over 6 over here. So there's actually an infinite number of solutions to this equation. And here's why, right? So I graphed both my function and then that line y equals 0.3, which is what we were solving for. And then here's my first solution. Here's my second solution. And then as we move on, time goes on, we get one solution every 2 pi, right? By the way, these first two are just 5/12 and 25/12 as decimals. So that's why when we're solving these, the convention is to give only the first two solutions rather than giving all infinite solutions, right? So you will often see for all values from 0 to 2 pi as the bounds for the solutions. Let's tackle one more example here. This one's a little bit harder algebraically, although it's certainly nothing we can't handle. The first thing I want to point out is we have this cosine squared x. So I want to make just a note of that. That is some notation we need to know. So cosine squared x written like that is the same as this cosine x all squared. And the reason we write it like that rather than how we might expect is if I write the squared by the x, it's unclear whether the squared is, x squared or the whole thing squared. So we write it on the cosine. So don't let yourself get confused by that notation. It's not that hard, it's just new. So I'm going to go ahead and isolate my trig function again. So I'm going to add 1 on both sides. And then I'm going to divide by 2. And then, because of what we just talked about, I want to take the square root of both sides to isolate my cosine, right? So I know that cosine is outside, or the square root is outside the cosine. So I get cosine of x equals, you probably remember this from working with quadratics, when I square root both sides, I don't get just plain old square root of 1/2, I get plus or minus the square root of 1/2. Because if I square the positive or the negative version, I'm going to get 1/2. So this already has 2 solutions, and it's about to get a few more, actually. The first thing I'm going to do is I'm just going to square root just the 1 is still 1 over the square root 2. And I'm going to just rationalize. I don't necessarily need to do this, but this will help me see what this looks like on the unit circle. Okay, so my equation now is cosine of x equals positive or negative square root 2 over 2. So now I'm going to go back to my unit circle, and here's where it helps to burn just as little brain power on the unit circle as possible. But if I have to look it up, here it is. And notice now I have 1, 2, 3, 4 examples. 4 solutions here. So they're all my 45-degree angles, or my multiples of 45 rather, on the unit circle are my solutions. And the reason I got so many solutions is because of that squared in my equation.